Okay, so hello everyone. Welcome to this session, and in this session we are going to discuss about the BJT in common emitter configuration. So it's the most preferred configuration for BJT to use as an amplifier. In this configuration, your input is applied between the base and the emitter, and output is taken from the collector and emitter. So we have used here symbolic view of NP and BJT, and with the proper biasing to make sure that base emitter junction is forward bias and base collector junction is reverse bias. All right. Okay, and this is the same diagram with the NPN structure form. Okay, so this will be helpful while explaining the working. So the BJT characteristics, the BJT behavior can be explained with the help of input and output characteristics. So let us start with the input characteristics. So input characteristics is between, you can see over here from this diagram that from the input side, VB is the input voltage and IB is the input current, whereas VC and IC are the output parameters. So input characteristics is between VB and IB with a constant VCE value. And we see a family of curves over here for two different values of VCE constant, and we are getting the curves. All right. Now we have to explain what these curves represent. All right. So if you see at the first glance that its characteristics is looking similar to the PN junction characteristics. Now since your base emitter junction, if you see base emitter junction is a PN junction, right? So if you are increasing the value of VBE, that means you are forward biasing the PN junction more. So more electrons will flow, will be emitted out of the emitter and reach the base terminal, and hence will be collected by the collector terminal. So as you increase the value of VBE, IB increases exponentially as expected for a constant value of VCE. Okay, because your base collector junction is reverse bias, so that will be able to collect the electrons at the collector terminal. Now, second thing is, as VCE is increasing, as you can see VCE increasing from constant value from red curve to the green curve. Your for the same value of for the same value of VBE, the IB value reduces. So as we increase the value of VCE, why does the IB is reducing? So that is what we are going to investigate right now. Okay. Now, one thing we can understand from here from this diagram that VCE, the total voltage, is nothing but VCB plus VB. Now, how this has come? See, VCB can be written as VCE minus VBE because its a emitter is common, so we can write this very easily. VCB is nothing but VCE minus VBE. So, what is VCE can be written as? VCE can be written as VCB plus VBE. Okay, I hope this is clear. So therefore, with a constant VBE value, if I increase the value of VCE, your VCB value also increases. Okay, so my collector base voltage also increases. So far so good. So as my collector base voltage increases, your collector base junction becomes more for reverse bands. Okay, so as my collector base junction becomes more reverse bias, so what will happen is, so as you can see, this is my collector base junction. Okay, my collector base junction become more reverse bias means what? Its depletion region width will increase. Okay, so depletion region, there is a depletion region formed between this N and this P region, right? So let me show that depletion region. Yeah, so the dark line red color one is the initial depletion region, and now due to increase in the value of VCB, your depletion region becomes wider like this dotted line, as you can see over here. Okay, so common base junction depletion region width increases. So what happens is the effective base width, so this is my base, right? So earlier the effective base width was this much WB, and now due to increase in the depletion region of of collector and base, the effective base width becomes reduces to WB dash. So WB dash is lesser than WB originally. So therefore, what happens is in the base, electron hole recombination takes place. So whatever electrons are been moving towards the base terminal, some of them recombine. So that probability of electron hole recombining in the base reduces even further. So due to this, what will happen? The most of the electron traveling from the emitter through the base will get collected at the collector. Most of them, because now base is becoming even smaller. I mean, the effective base weight becomes even smaller. So probability of these electron hole pair getting recombining is reducing. So most of the current, will I mean most of the electron will be traveling towards the collector, will be collected, and at the same time the base current will reduce. Okay, because the probability of forming electron hole pair is reducing. Therefore, the base IB current reduces. Base current reduces. So therefore, in short, we can what summary we can say that as VCE is increasing, IB or the base current reduces. That is, the curve shifts towards the left hand side. Okay, so this is the conclusion. Now, from this input characteristics, we can determine an parameter which is called as the input resistance. So what you do is you take the slope. This is an exponential curve. So small segment of exponential will be almost a straight line. So from there you can take the slope. So it will be x-axis will be variation will be delta VB and y-axis variation will be delta IB. So delta VB upon delta IB will give us the input resistance. So as you can see, delta VB value is very small change and delta IB value is a pretty large change, but it's in microamperes. So the Rn will be quite large value in kilo ohms. Okay, and this is done at a constant value of VCE. So from the input characteristics, we can determine that Rn value, input resistance in common emitter configuration, it's a pretty high value. It's in kilo ohms. Okay. Next is the output characteristics, which is pretty important and very vital to understand the working of BJT in common emitter mode. So output characteristics is the characteristics is the plot between the output current IC and the output voltage VCE. As you can see over here on the right hand side of your screen, VCE versus IC for different values of input parameter constant, which is IB. So for how can we keep IB constant? By keeping VB constant. Okay, simple as that. You keep voltage constant, your current will be constant at the input. So for the different values of IB constant, you get a family of curves as you can see over here, and from here we see three operating regions: the green one, the yellow one, and one written as 2. So the entire red color mark over here, it's the 2 operating region. So the region marked as 2 is the active region. Okay, so in between space between the yellow and the green color is my active region. The yellow color region is the saturation region and the green one is my cutoff region. Okay, so we have to explain the behavior of uh, the the BJT in these three operating regions. Okay, in common emitter configuration. So let us understand the working one by one. All right. Okay. So let me consider over here. Bring the screen so that I can operate easily. Okay. So, okay, fine. So let us concentrate on this diagram. Now we are concentrating on the active region. So what is happening in the active region? First of all, we'll explain. So as we slowly increase the value of VCE, uh, your IB value, your IC value go on increasing. Okay, at a steady pace. It's almost constant and it goes slightly increases in its value also. Also for the different values of IB is increasing, your IC also increases along with it. Okay, so as you can see, IB is in microamperes, so IC will be in milliamperes. They are related by a current gain factor which is beta, as we know already. All right. So your as your VC is increasing, your IC value also increases slightly. It's almost like a constant, but it's increasing slightly. So we'll try to understand why it is happening in the active region and why with the increase in the value of IB, your IC also increases. That is very obvious from IC equal to beta IB expression. Okay, so in the active region, basically as your IB increases, your IC increases. This is due to the fact that IC is the output current, IB is the input current, and beta is the current gain factor, which is relating the two, and it's very much higher than around 100 to 200. So IC will be definitely higher because as we increase the value of IB, IC also increases. Very obvious. Now the second reason is that why with the increase in value of VCE, IC increases slightly. So let us try to understand that now. Okay. Okay. Wait a second. So what are we explaining? We are explaining the fact that why does the with the increase in the value of VCE, the IC value slightly increases. All right. So let's get back to this diagram and explain it. So we know that VCE is VCB plus VBE, right? Now VB being held constant, it's constant, right? Because IB is constant. As we increase the value of VCE, your VCB will increase, right? Your base collector voltage will increase. Now, as we know, let me go back to this only now. As your VCB increases, your collector base depletion layer width increases. Now we have explained this before, right? This is my earlier older one. This is my earlier depletion region, and now due to increase in the value of VCB, the depletion region is even becoming wider. This dot represented by this dotted line. So what is happening is the effective base width is going on reducing. So if the effective base width is going on reducing, the IB contribution to the current flow will reduce as less number of electrons will recombine at the base with the holes in the base region, right? So most of these electrons will be traveling via the base, will be collected by the collector. Okay, as you can see, most of these electrons, now since the base width has reduced, only some of them will recombine and most of them will be collected at the collector. That is the reason why as your VCE is increasing, your IC increases slightly with it. Okay, and the point to be noted is that the BJT is used as an amplifier in the active region of operation of BJT. All right. Now let us also determine the relation between them. The IB is the input current. We have determined that, and IC is the output current. So we have beta DC, which is IC upon IB, which is the DC current gain, common emitter current gain, and there is a beta AC also, which is delta IC upon delta IB. They are almost the same. They might seem differently, but if you see carefully, they are almost in the same range. Okay, all right. So far we have explained the working of your operation of BJT in the active region. Now let's go to the saturation region. Okay, let's go to the saturation region and explain what is happening. Okay, fine. So this is again we are back to the output characteristics. So what we do in the saturation region, we reduce the value of VCE to a very low value close to zero. Okay, so as the value of VCE is reducing, your IC value reduces towards, with it very rapidly, and it goes to zero. So as we come in this region, as we decrease the value of VCE further, the IC value decreases rapidly and goes towards the zero. Okay, now we have to explain why this happens. Okay, so let us again go to the working uh, of it in detail. So in the saturation region, as the value of VC is reducing, now we know that VC is VCB plus VBE, right? Let's consider VB is a constant because IB is a constant. So as you reduce the value of VCE, your VCB value also reduces, right? That means your collector base junction, here it is, your collector base junction is becoming more and more lesser and lesser reverse bias, and finally at a very low value of VCE, your collector base junction becomes forward bias. Now base emitter is also forward bias, base collector is also becoming forward bias. So as soon as the collector base junction become forward bias, electrons will not reach the collector now because it is forward bias, right? So therefore your IC current reduces to zero as your VC being reduced to a lower value rapidly. Okay, and we say that the BJT is operating in the saturation region because if this becomes forward bias, okay, if this becomes forward bias, the polarity, base, imagine the base collector region becoming forward bias. So what will happen due to it? The electrons which are here will try to diffuse on this side, will try to come towards the base side, right, instead of going towards the collector side. So that is the reason why the electrons are not reaching the collector terminal, the collector region, and hence they are not contributing to current flow. Therefore the IC value drastically reduces to zero as seen from the output characteristics over here. Okay, as we reduce the value of VCE to a lower value, right, the IC value drastically falls to zero value. Okay, so this is the region of operation where BJT operates as a in the saturation region. Okay, okay, now the cutoff region. Now as you can see, the cutoff region is the curve, the region of the curve where IB equal to zero curves below the IB equal to zero. So you see there is slight current. IC is not equal to zero. It's so we'll understand what is the value is. So yeah, let us try to understand it. So NPN BJT operates in the cutoff region when IB is equal to 0. Okay, but here the IC is not equal to 0, as you can see very clearly denoted by the green region of the curve. So what happens is when IE is 0, the leakage current was given by IC equal to ICBO. So IC was equal to actually um, IC was alpha IE plus ICBO, right? We can call this equation number 1. But IE is IC plus IB, that is what the terminal current means. So IC will become alpha times IC plus IB plus ICBO. Okay, so if you take this alpha IC on left hand side, we get 1 minus alpha IC is equal to alpha times IB plus ICBO. So we take this 1 minus alpha, divide numerator and divide left hand side and right hand side by 1 minus alpha. So you'll get IC equal to alpha upon 1 minus alpha into IB plus 1 upon 1 minus alpha into ICBO. So we know already previously that alpha upon 1 minus alpha is termed as beta. So IC will be beta times IB plus 1 upon 1 minus alpha times ICBO. Now we know in the cutoff region IB is 0. Alright, so we substitute IB equal to 0 over here. So this will be equal to 0, IB will be equal to 0. So IC will be approximately equal to 1 upon 1 minus alpha into ICBO. Now 1 upon alpha is very small value, very close to 1, right? So this term will be a very large value, and we know beta is alpha upon 1 minus beta. So if you add 1 to it, you will get 1 upon 1 minus alpha. So what we can say is IC is approximately equal to 1 plus beta times ICBO. Now ICBO is in nano amperes, right? It's a leakage current. So the value of leakage current at IB equal to 0 is called as ICEO. We call it as a collector to emitter leakage current with base open. Okay, and that ICEO is nothing but 1 plus beta times ICBO. That is why we see that the leakage current is slightly more in the common emitter configuration when the BJT is in the um, uh, you know in the cutoff region. Okay, so in this region of operation, when the BJT is in the cutoff mode, IC is basically the small current which is flowing is nothing but ICEO, that's the leakage current, and that's its 1 plus beta times ICBO, which is in the common base configuration leakage current. All right, now, yeah, these are the various from the output characteristics we can determine the output resistance, as you can see, right? So output resistance is delta VC upon delta IC. So delta VC is a large variation and delta IC is in milliamperes. So it's a pretty large value again. R out is in kilo ohms for common emitter configuration at a constant value of IB. All right. So R out can be determined from the output characteristics. Now, what are the main properties of common emitter configuration? We get a moderate current gain, which is beta, moderate voltage gain, right? Moderate input impedance and output impedance. They are pretty not very low and not very high value, moderate value, but we get a very high power gain, right? So this high power gain is the reason why it is mostly used as a preferred configuration for BJT as a voltage amplifier. Okay, so yeah, that's it for this session. Next time we'll start with common collector configuration of BJT. So thank you.